Then you had your exothermic reaction, which were your combustion reactions, respiration, nuclear reactions that are exothermic. So, and we also discussed a few things that a reaction produces. I told you produces work in two ways, or produces output or useful energy in two ways. One is that it produces heat. This is what we measure when we talk about enthalpy change. That's the net energy change that is either released or taken in. You burn a mass, it produces a lot of heat. So I told you that this is what we're going to study. We're going to study that a reaction produces work in the form of heat, or takes in work in the form of heat. There was another thing which was entropy change or disorder. A reaction, you could have a firecracker, it could explode, and that would be producing a lot of work as well. But it may not produce a lot of heat, but it may produce a lot of work because a lot of disorder would be created. But we're not going to study that. Is for A2. So we're going to talk about the heat of the reaction. That is the energy that is taken in or given off in a reaction. Now, just 1 second. So now this one. This is what we were studying. I told you that whenever you have a reaction, two things would happen. Old bonds would be broken, and they need to be broken. That would require a minimum actuation energy would be needed. So there's a minimum amount of energy that would be required. So we can write that minimum amount of energy. Energy that would be needed. And that minimum amount of energy would be known as the actuation energy. So why do you need this actuation energy? You need this actuation energy. You want the molecules to be energetic enough so that when they bump into each other, they bump into each other forcefully. And when they bump into each other, they collide with each other very effectively, the old bonds are going to be broken. So you want the old bonds to be broken. So for example, there's a piece of paper and there's oxygen in the air. Why do they not react? Why doesn't paper burn on its own? Because the molecules are not bumping into each other with enough force. Which is why if you want to burn a piece of paper, the first thing is you heat it up. You put fire next to it. You heat up the molecules so that the molecules, they collide with each other with enough force that the old bonds, they get broken. That's the first thing. And once that happens, then new bonds can be formed, and that releases energy. So what we can say is that usually a reaction involves two things. So the net energy change of a reaction, which is the enthalpy change of the reaction, would be energy that would be required for bond breaking. So that part is endothermic. So that part would be endothermic, and that will have a positive sign. And then there would be energy that would be released during bond formation. So that part, so that part would be bond formation, and that is going to be exothermic. So you'll have energy that would be taken in for bond breaking, and there would be energy that would be released during bond formation. One of the part would be endothermic. The other part is going to be, that one is going to be exothermic. Now that gives us the first formula for enthalpy change, for calculating the net energy change of a reaction. Remember this, every reaction, two things would happen. You would have to break the old bonds, and then you would have to form the new bonds. So for example, we'll try and do one example, and we'll try and figure out how many bonds are broken and how many bonds are formed in a particular reaction. So for example, I've got an H2 molecule. I'm going to take a simple reaction. I've got an H2 molecule, and it's reacting with the Cl2 gas molecules, and together they are reacting, and they're forming HCl molecules, two of them. So that means what bonds need to be broken in this reaction. So I'm going to list the bonds that are broken. So the easy way is to break all the old bonds. So what you're going to do is you're going to break the HH bond over here. That needs to be broken. So that needs to be broken. And you need to break the CL-Cl bond as well. That needs to be broken as well. Once those bonds are broken, the new bonds are going to be formed. So what bonds would be formed? So look at the products and form any bonds that are present in the product. So it's basically the bond between H and Cl that's going to be formed, and there are two of them. So you would have to be you would have to be forming two of the HCl bonds that need to be formed. Now the energy that would be involved for this, it would be endothermic, so that would all be in positive, and the over here it's going to be exothermic, that would all be in negative. So it's going to be the energy that would be required for bond breaking and energy that would be released during bond formation. So when you're thinking of breaking bonds, break all the bonds in the reactants. And when you're thinking of forming bonds, then what you're going to do is form all the bonds that are present in your products. So in this case, you'll have these bonds being broken and these bonds getting formed. So your enthalpy change is going to be, you'll just apply the formula, which is the overall enthalpy change would be you sum all of this up, sum all of it up. The amount of energy that is taken in during bond breaking and the amount of energy that is released during bond. So bond breaking is you're going to need energy to break one HH bond. That would be endothermic. You would need energy to break the CL-Cl bond. And energy would be released. That would be exothermic when you form two HCl bonds. So that is going to be your enthalpy change. All you need is the amount of energy that is needed to break the bonds and the amount of energy that is needed to form the bonds. So that is how enthalpy change is going to be. That is how enthalpy change is going to be formed or found out. One second, let me. So that is how enthalpy change is going to be found in different reactions. Now for this, all that is missing is you have to find out the energy that is needed to break bonds and the energy that is released during bond formation. Now, that energy is called bond energy. So in the lab, people have actually calculated this bond energy. The first thing is you have to learn the definition of what bond energy is. So bond energy by definition is the energy that is needed. It's the energy that is needed to break one mole of bonds of the same type. Of the same type. And so 1 mole of bonds of the same type and in gaseous molecules. So if you want to break 1 mole of HH bonds, that would be the energy that would be needed for that. That would be bond energy of HH. If you want to break 1 mole of CL-Cl bonds, the energy that would be needed would be known as the bond energy of CL-Cl. Now, based on the definition, there's one problem with this definition, that the bond energy is only defined for gaseous molecules. So make sure, remember this. It's only defined for gaseous molecules. So that leaves us with a problem, and that problem is that what if the substance is a solid or a liquid? Then you can't use this method, because bonds broken minus bonds formed, you can't use this method. And the reason you can't use this method is because bond energies are only defined for gaseous molecules. So if you have water, which is liquid in the reaction, you can't use bond energies because bond energies are not calculated for liquid molecules or for solid molecules. So here's a problem with bond energies. So I'm going to go back to the formula which I wrote down. And we're going to talk about this formula and the limitation for this formula, which is that this one can only be used, or this method can be used only for gaseous molecules. So if equation contains solids or liquids, so if our equation contains either solids or liquids, then we can't use this formula because we won't have the supporting data with us. So the idea is simple. Take any reaction, like the reaction over here. Take this reaction, figure out how many bonds need to be broken, and break all the bonds in the reactants. And how many bonds need to be formed? Form all the bonds that are present in the products. The bonds that are broken, that's endothermic. The bonds that are formed are going to be exothermic. The bonds that are broken will have positive signs. They would be endothermic. Their energies would have a positive sign. And the bonds that are formed, their energies will have a negative sign. They would all be exothermic. So the thing is, you just add them all up. Formation would be exothermic. Breaking bonds would be endothermic. You'll have a data booklet. From that data, you will be able to calculate the values of this. So you need bond energies. Bond energies are defined for gaseous substance, and that's the only limitation. So the equation, all of them have to be in gaseous state. Otherwise, you can't use bond energy. So I'm going to open the data booklet now. Now, in your exam, they've recently changed something that they're no longer going to give you data booklets. What they'll do is the data booklet would be part of your exam. So it would still be there. I mean, the data would still be there, but it won't be a separate booklet. So just remember that this data would still be there. So if you look at the data booklet, previously in the previous exams, they gave a separate booklet, which was separate from the exam. Now this data booklet would be part of the exam. So look over here. There are bond energies values given. So for example, if you want to break the HH bond, the value is already provided here. If you want to break the nitrogen, I think this is the triple bond of nitrogen. So the value is already given. So if the bond is really strong, the energy is really high. You want to break the P triple bond P, that's 485. You want to break fluorine bonds, that's 158 kilojoules. So the amount of energy that is needed to break any of the bonds, that's provided over here. Also remember, there's a word called homonuclear used over here. That simply means that it's a bond between the same type of atoms. Like it's a bond between oxygen atoms. So that's homonuclear. Heteronuclear means that it's a bond that's between two different atoms. Doesn't really matter. It's just, they're just fancy words used for these. So for example, if you're breaking the HF bond, that requires 299. So that kind of indicates it's a very, very weak bond. You've got a carbon monoxide molecule. That's a pretty strong bond. And then there are other values as well, which are known as average values because these are average values because not all carbon-carbon bonds are kind of exactly the same. So these are average values. Not all carbon double bond, because these bonds are present in big complicated molecules. So all molecules are kind of slightly different from one another. So these are average values. So the CH bond, remember, all the carbon and hydrogen bonds are not exactly the same. So which is why these are average values, but they kind of represent the same thing. So all these bonds and the energy that is needed to break those bonds, these values are provided. So what I'm going to do now is, I think Yatak clear. Is this clear? Maz, is this clear? Ahmed, Izan, is this clear?
Yes,
Raheel?
sir.
So what I'm going to do now is I'm going to use this data booklet. Okay, just remember 9701. Just write the code 9701 and type data booklet. You'll find a PDF of the data booklet. So I'm going to go back to the question. I wanted to find the enthalpy change for this reaction. So all I had to do was I had to break this HH bond and the ClCl bond. That is endothermic. So I'm going to try and find the values of these. So if I go back into the data booklet, HH and ClCl is 242. So I'm going to use that. So ClCl is 242 kilojoules. And let's find the other one, which is HH. That's 436. So to break the HH bond, that requires 436. So that's also given. And then I would have to form two HCl bonds. Remember, the bond energy is always defined for 1 mole for one bond. For two, you just have to multiply by 2. So we're going to find HCl now. HCl is over here. That's 431. So we're going to try and find HCl. That's 431, and that is going to be multiplied by. It's going to be multiplied by 2. And if I use my calculator, I'll just open the calculator over here. Actually, I don't have. One second. Where's my calculator? Justice. Okay, I've got my calculator. So all I need to do is it's 436. So 436 plus 242, and then it's minus. I'm going to use brackets. 431 times 2 bracket closed, and that's giving me. It doesn't look like the right value. Can anyone do this? 436 plus 242 minus 431 times 2. Not really sure if that is the correct value.
Minus 184, sir.
Minus 184, TK. But the desktop calculator is messed up. So it's minus 184 kilojoules per mole. So it's a simple way of finding the enthalpy change of a reaction. So minus 184, TK, that's fine. Now, the only trouble is you would have to count the bonds really carefully. So for example, if I give you a complicated question, so remember one thing, when you're doing this, bonds broken, break all the reactant bonds. Bonds form all the bonds that are present in the products. So let's try and do a slightly more complicated question. And let's say we talk about, because you would have to count the bonds properly. So question number 2, let's do another example. The method is simple. The only thing is, and remember, this is always in all energetics questions, you have to be very careful with your calculator, because there's going to be a lot of positive things getting added and a lot of negative things taken out. So make sure you're good with your calculator. So question number 2, let's do this one. So let's say I've got an ethene molecule. So I've got C2H4, and it reacts with water and hydration happens. Okay, so if you know some of your O-level stuff, it ends up forming C2H5 and OH. Now, in a lot of questions, they won't give you what the structure is. You would have to figure out the structure on your own. So for example, C2H4, that's an alkene. I mean, you're going to do organic chemistry later as well, but these are things that I assume that you have studied in O-levels and you know this. So that's an alkene. It reacts with water. So remember, water is an oxygen bonded to 2 hydrogen atoms. And it ends up forming an ethanol molecule, which is C2. And there is H5. So 5 H's bonded to it. And there is an OH as well. So there's an OH as well. Now, a slightly more complicated molecule, all you have to figure out is, remember reactants. Break all bonds that are present in the reactants. So bonds broken, you just have to list them down. So bonds broken, that would all be positive. Bonds broken, how many bonds are broken? So first one, CH bonds. The number of CH bonds that are broken over here, that is, if you count that, that's 4 of them, 4 C and H bonds, 4 of them. So that would be multiplied by 4. How many, remember think of the double bond as one thing, because if you look at the data booklet, you're given the energy to break the entire double bond. So don't think of it as 2 separate bonds. It's one double bond. That's it. So you would have to break the double bond, carbon, double bond, carbon. That needs to be broken, only one of them. And then you move towards this one. How many O and H bonds need to be broken? There's one O and H bond over here, and there's another OH bond that's over here. So you need to break 2 of them. So you need to break 2 OH bonds. And then you're going to form bonds. In the products, you're going to form, whatever is present in the products, form all those bonds. So we're going to try and form all those bonds in products. So bonds formed. So bonds formed. How many CH bonds? That's going to be 1, 2, 3, 4, and 5. So you've got 5 C and H bonds that are getting formed. So there are 5 of them getting formed. How many C and C bonds? That's 1. So I've got one CC bond. Then I've got a C and O bond. That needs to be formed as well. And finally, I've got one OH bond. So the OH bond needs to be formed as well, just one of those. So, that's the tricky part. Because there's room for a lot of silly mistakes here, because you have to make sure, do this very carefully, because you're going to miss just one bond and the whole answer would be incorrect now. So I'll just quickly go this: 4 CH bonds, 1 double bond, 2 OH bonds. So that's fine. 5 C and H bonds that are going to be formed, 1 CC bond that's going to be formed, 1 CO bond, 1 OH bond. So that's also fine. Bonds broken is endothermic. So that is all going to be plus. And bond formed is all going to be, all of them is going to be exothermic. So all of them would be negative. So you just sum them all up. So a few things would get cancelled out, like the CH. I'm going to cancel that even before I start. 4 CH and minus 5 CH. So that would be left. That would give me just 1 CH over here. There's 2 OH minus 1 OH. So that just leaves me with 1 OH. Is this clear? Yes or no? Is this clear?
Yes.
Yes.
So I'm going to just add up copy the values from the data booklet and add them all up. But be very careful. Just for I've just simplified this. Plus 4 CH minus 5 CH. So that's 1 CH minus 1 CH. 2 OH minus 1 OH. That leaves me with just 1 OH. So I'm going to add C double bond C into 1. So what is C double bond C? That's 610. That would be into 1. So 610 times 1. Forget times 1. Just 610. And it's going to be plus. The next one. OH. That is 460. That is given somewhere over here. Not sure where. This one. OH is 460. So I got one OH. So that is 460. The rest is minus over here. 1 CH. CH is I think it's where's CH? 410. CH is 410. So that's minus 1 CH, so that's minus 410. And then there's minus CC. What is C and C? That's 350. So that one is 350. And then you've got minus C and O. What is minus C and O? That's this one, minus 360. So that one is minus 360. So I think I did not make any mistake copying this. All I have to do is, remember, bond breaking is all endothermic, all positive. Bond formation is all exothermic, all negative. So what do you get when you solve this? क्या बने क्या?
minus 50.
Minus
50.
kilojoules per mole. Acha, can anyone just confirm, is this minus 50? Because remember, I'm going to keep on repeating that energetics questions, they look simple, but there's a room for a lot of mistake. A lot of mistake in the addition and the subtraction. So two people are getting minus 50. So I think that is
Yes,
correct.
it is. It is minus.
Just remember, even a simple calculation like this, you can get it wrong on your calculator. So you have to be very careful. Make sure you pay attention to whatever buttons I mean, just do it slowly. Even the counting the bonds, you make mistakes. People make mistakes with that. So the thing with the energetics questions is, especially bond energy questions, is very easy to get them wrong. Very easy. People do everything wrong. They just miss either one bond, or they just forget one sign, or they add one sign incorrectly on the calculator, and the whole question gets messed up. So because there are lots of small parts to it, so lots of room for error. Silly mistakes.
Okay.
Now, question number 3. Let's do another one. What we can do is we can just jump to past paper questions related to bond energy. So past paper questions, 1 second. So we'll just jump to bond energy questions, which are, it doesn't even see where bond energy is. This one. So for example, this one, let's try and do this question. Now, if you look at this question, what it states is, you just have to figure out the enthalpy change for this particular reaction. That's it. Not that complicated, just the enthalpy change. So how many bonds are broken? So I'm going to write bonds broken over here. So 2 CH bonds. I got a triple bond in the middle, so that's 1 C triple bond that's going to be broken. And I'll have, this one is a double bond, so it's 2.5 O2 double bonds. 2.5 of them. And in the products, I'm going to form these bonds. So I've got a water molecule. So water molecule is this thing. And I've got 2 carbon dioxide molecules. Carbon dioxide is 2 of them. These are getting formed. So how many bonds in the water molecule? Bonds formed. So this one is going to be 2 OH bonds that are going to be formed. And you'll have how many C double bond O's are getting formed? There are 4 of them. Remember, there are 4 of them. That's a C double bond O. That's another C double bond O, C double bond O. So that's 4 of them. And there are 2 OH bonds. So 2 carbon dioxide molecules, 1 water molecule. So that's the total number of bonds broken and formed. So we'll just start adding the values. 2CH, that's 410 times 2. Positive. Bonds broken is endothermic. C triple bond C, that is 840. That's given over here. That's 840, and there's only 1 of them, so that's plus 840. You got an oxygen double bond oxygen, that's 496 times 2.5. And then bonds formed. You got OH bonds, which are going to be, where's OH? That's 460. That would be minus. And you got C double bond O, which is given over here. That's 740 times 4. So just add all of them up. I mean, on your calculator, start doing this. Bonds broken plus 410 times 2, plus 840, plus 496 times 2.5, then minus 460 times 2, and minus 740 times 4. Can anyone tell me what the answer is?
C.
Which one? C?
A.
A. Minus 980. Can anyone confirm, is this minus 980? I think it's minus 980. I'm not. Minus 980. It looks like minus 980. Mask kiya ye? Ahmed, Reed, have you done this, Hospa? Sidra?
I got A as well.
Okay, that's fine. It's A. I leave the tricky questions for later. I mean, like not right now. I'll do the easy ones first. So let's try and do this one. Let's try and do this one. It says the reaction which causes the presence of oxides of, I mean, you've got a reaction here. And he's saying, what is the bond energy in kilojoules per mole of the bond between the NO atom? So remember, the enthalpy change is already given to us. How do you calculate the enthalpy change? You calculate it by figuring out the bonds that are broken. So I'm gonna list the bonds that are broken first. So bonds broken, that's I mean, N2 has a triple bond, so you need to break that triple bond. So that's one of them. And oxygen has a double bond. So I need to break that. And then I need to figure out the bonds that are formed. So that is two NO bonds that are formed, right? I have no idea what that is. I mean, this is what we have to figure out. The N triple bond N value is given in the data booklet. That's given as like if you look at the data booklet, somewhere they have homonuclear. This one is in. This one is in. That's not N triple bond N. Oh, where's N triple bond N? Probably in the previous page. You got an N triple bond here. That's 944. So that is given. So I'll just write it over here. So bonds broken. So the enthalpy change is basically bonds broken, which is plus 944, because you would have to break the N triple bond N. And then you would have to break the oxygen double bond oxygen as well. So the oxygen double bond oxygen is given over here. That's 496. So that is also provided. That will be plus as well. And minus bond formation. Bond formation is going to be exothermic. So you're going to break these two NO bonds whose value you're not sure of. So you want to break those two NO bonds as well, right? But that is going to be exothermic. Now the enthalpy change is already given to you. It's 180. That's already provided to you. So the enthalpy change, I mean, you already know the answer already. So that is what? It's plus 180. So we know what the answer should be. So I can figure out the NO bond energy by just solving for the equation. It's going to be 180. I mean, I need to bring the NO to this side. So it's going to be 2 NO. It's going to be 944 plus 496. Rearranging all the terms, that's minus 180. And then I'm going to take the 2 and divide everything by 2. So is this clear? That the enthalpy change would be break these bonds, form this bond. This would be your enthalpy change. So in this case, the only thing was that the enthalpy change was already calculated for you. One of the bond energy was missing, and you just have to find this. So tell me what the value is. What do we get for this? I say in this case, I'll just
630.
in this case, I'll warn that none of the four options. So this one is coming out to be equal to 630, right? Kilojoules per mole. So it's coming out to be 630, right? That's fine. Now the answer is A actually. So you'll wonder why the value is different. So why is the value different? Why is it coming out to be 655 over here and you're getting 630? So the problem is that the problem is with the data booklet, because remember, the data booklet I've opened is the one that was printed in 2021. The question belongs to 2012. Like it's a 10-year-old question. So the thing is that 10 years ago, Cambridge had slightly different values in the data booklet. In the recent data booklet, the values are slightly different. So just don't worry when you solve past paper questions. Some of your answers would be slightly off, and the reason for that is because the data booklet values are kind of always like, I mean, if you're trying to solve a question that's 10 years old, the options would not be exactly the same because the values would be slightly different. Especially some of the values would be like, I mean, they slightly change in 10 years. So that is why there's this small error that's coming, but that's not your fault. That's the fault of them changing the data booklet values, right? Is that clear?
Yes.
Chalo, let's try and solve more bond energy questions, and then we'll and I've been skipping some questions which are slightly harder. So we're going to try and solve those questions. But remember, the formula is simple. The only limitation is you can only use bond energies if the molecule is gaseous, or if the question specifically demands that it should be, I mean, you should solve it using bond energies. But otherwise, there's this limitation. Like if a substance is liquid, you can't use bond energies. If a substance is solid, you can't use bond energies. Otherwise, the formula is really simple. And you just have to be very careful about the calculations. Let's continue with more difficult questions on bond energies tomorrow then, okay?
Sir,
Anji.
so can you upload this recording, today's recording on Drive?
हाँ ठीक है, मैं वो भी share कर देता हूँ, ठीक है?
Okay, sir. Thank you.
Okay, take. Allah Hafiz.
Sir?
Allah Hafiz.
Hafiz. हाँ जी.
सर इसकी कोई एक्सप्लेनेशन है कि मतलब हमें वो ये गैसियस मॉलिक्यूल्स में क्यों होने चाहिए बॉन्ड एनर्जी के लिए?
उसकी कोई एक्सप्लेनेशन नहीं है. उसकी एक्सप्लेनेशन ये है कि जो डेटा बुकलेट है ना, जब वो बॉन्ड एनर्जी, when they were measuring bond energies, they were doing it for gaseous molecules. That's it. तो डेफिनेटली दुनिया के अंदर ना एक डेटा बुकलेट होगी जहां पे लिक्विड मॉलिक्यूल्स के बॉन्ड्स तोड़ने के लिए भी बॉन्ड एनर्जी होगी. और what I'll explain that I'm going to explain this a bit. जैसा वाटर का मॉलिक्यूल है ना, उसके बॉन्ड्स तोड़ने, राइट? लिक्विड वाटर के अंदर, रिमेंबर लिक्विड वाटर के अंदर इट्स नॉट जस्ट बॉन्ड्स, बट liquid water molecules के अंदर ना कुछ और भी होता है in addition to bonds, and that is the intermolecular forces that is keeping them in liquid state.
सर, जो एंथैल्पी चेंज होता है वो यूज हो सकता है लिक्विड और सॉलिड्स के लिए, या वो भी सिर्फ गैस के लिए होता है?
नहीं, क्या एंथैल्पी चेंज? नहीं, एंथैल्पी चेंज लिक्विड और सॉलिड्स के लिए किसी और तरीके से मेजर करना पड़ेगा, नॉट यूजिंग बॉन्ड, क्योंकि बॉन्ड एनर्जी जो है ना वो डिफाइंड ही नहीं है लिक्विड के लिए ना. अब मैं इस पे एक्सप्लेन भी कर दूं कि व्हाई नॉट लिक्विड्स, क्योंकि लिक्विड्स के अंदर अगर आप ओवर एज का बॉन्ड तोड़े हो ना, लिक्विड्स के अंदर बॉन्ड्स के अलावा इंटरमोलेक्युलर फोर्सेस होती हैं, वो भी तोड़नी पड़ती हैं. ठीक है, तो इसलिए ना वो जो एनर्जी की वैल्यू होगी ना वो गलत आएगी, क्योंकि इन लिक्विड स्टेट यू नॉट जस्ट ब्रेकिंग बॉन्ड्स, यू आल्सो ब्रेकिंग, क्योंकि वो लिक्विड आपस में जुड़े हुए होते हैं ना, तो इसलिए उनके बीच में जो इंटरमोलेक्युलर फोर्सेस है उनको भी तोड़ना पड़ता है. ठीक है, रही ये क्लियर है? चलिए ठीक है. चलिए ओके देन, लेट्स डिस्कस टुमारो देन. ठीक है, ओके अल्लाह हाफिज.
Thank you.